So you want to speed up your software so that it's capable of running even the most sophisticated audio algorithms in real time. How to achieve that? Well, this question has multiple answers, but one of them is definitely data alignment, which is the topic of today's video. Hi everyone, this is Jan Wilczek from thewolfson.com, and today I want to explain how to take advantage of proper data alignment. To present the full picture, I will introduce the relevant C++ features. To understand the concept of data alignment, we need to differentiate between address alignment and datum alignment. Let's imagine that computer's memory consists of drawers. Each drawer is of the same size in bytes, which is equal to a power of 2. And we can somehow choose which power it is. For example, the whole memory could be made up of 4-byte blocks. We can still address every byte, but only the first address in each block is said to be aligned. That is address alignment. Now, if a 4-byte variable is placed completely in one of these 4-byte blocks, it fills all 4 bytes of a block, it is said to be aligned. That is datum alignment. Now, how would it look like if such a 4-byte variable would not be aligned? It would occupy more than one block. It would cross the block boundary. For example, it could be placed at address 4n plus 1, when n is a non-negative integer, and would hence take addresses 4n plus 1, 4n plus 2, 4n plus 3, and 4n plus 4, which is equal to 4 times n plus 1. In order to read out such a variable, the processor would need 2 read operations, one from the first 4-byte block and another one from the second. That is, of course, slightly slower, but may as well be prone to race condition, where one thread reads out the first part of the variable, then another thread modifies the whole variable, and the first thread reads out the other part of the variable. In effect, the read out value is completely incorrect. So address alignment with respect to some power of 2 relates to this address modulo 2 to that power. On the other hand, datum alignment relates to whether a particular datum lies at an aligned address. A 1-byte variable, typically a char in C++, is always aligned. A 2-byte variable, typically a short in C++, in order to be aligned, must lie at an address divisible by 2. A 4-byte variable, typically an int in C++, in order to be aligned, must lie at an address divisible by 4, and so on. This specification of a particular type is called alignment requirement, which could be described as what's the size of the box the type should be placed in order to be aligned. How to ensure that your data is aligned? Well, in most programming languages, including C and C++, the compiler does that for you. That, however, may mean that your structures take up more space than is required because of the additional padding inserted to make your struct's data members aligned. That results in potentially unnecessary increased memory usage. Of course, one could argue that in modern computers such micro-optimization is unnecessary. Well, let's look at an example, shall we? Consider the following structure. A consists of a char, a short, an int, and another char. In memory, the structure looks rather like the following, due to data alignment done by the compiler. First we have the char, then 1 byte padding, then the short, then the int, then the char, and at the end another 3 byte padding. On my computer, size of A returns 12, what means that due to additional padding, struct's size is 4 bytes larger than the sum of its data members' sizes. The alignment of A is 4 because of the int data member. Int's alignment is 4, what determines the alignment of the whole structure. In other words, the int data member must lie at a 4 byte boundary to be aligned. This layout of A results in 4 bytes wasted per each variable of type A. That means that having an array of 1024 A's wastes 4 kilobytes of memory. It may seem an artificial example, but it is worth keeping in mind. What can we do to get rid of the padding? We could use some nasty implementation-specific preprocessor directives, which I will not utter here.
The language is that of Mordor, which I will not utter here.
As already mentioned, forcing data members to be unaligned can increase their access time. However, in this case, we can simply reorder data members of the struct in the following way. First an int, then a short, and then both chars. In struct B, int is at a 4 byte boundary, short at a 2 byte boundary, and of course both chars at 1 byte boundaries. It is worth mentioning that although B's alignment requirement is the same as A's, its size is 4 bytes smaller. A simple rule to follow in data member order declaration in order to minimize additional padding is to declare data members in descending order of their size, as returned by the sizeOf operator. We then get the best alignment we could possibly ever get with any ordering. Sometimes a loss is inevitable, as in the following struct. In struct C we have an int, 2 shorts, and a char, which is followed by a 3 byte padding. If we wanted to pack variables of type C in an array in a way that uses no additional space beyond the sum of C members' sizes multiplied by the number of array members, the only option left is to use the preprocessor directives. Along with the development of C++, more and more alignment features are part of the standard, rather than implementation-specific extensions. Let's look at each of them in turn.
Align_of keyword returns the alignment requirement of a type in form of a value of type size t. How the address of the variable of given type has to be aligned so that this variable is aligned. Align_as keyword allows to specify the alignment requirement of a type or particular class data member, how it should be positioned in memory by the compiler to make it aligned. It comes in handy when we want to align structs, for example, for using intrinsic vector instructions where data has to be 16, 32 or 64 bytes aligned. Mind you that the specified alignment can only be a power of 2 and, unless it's greater than the natural alignment, it will be ignored by the compiler. Alignment of template. class template that provides similar information to the align_of keyword. The difference is that it can be used in meta-programming facilities. Alignment_of_v template, helper template for alignment_of template that directly returns the value of alignment, so that alignment_of template with brackets, alignment_of_v template, and align_of are always equal. Align function allows the user to ensure that given pointer points to an aligned address with respect to given alignment number of bytes and indicated available space. Aligned storage, a simple wrapper providing uninitialized aligned storage space. As with any uninitialized storage, it requires construction at an explicit address and explicit destructor invocation at that address. May be used for a container type implementation. Aligned union, as the above, with the difference that the alignment suitable for all given types is chosen and the size of the allocated space is such that it can hold any of the objects of those types. Max aligned T type, an implementation dependent type whose alignment requirement is at least as strict as that of any scalar type, typically as large as long doubles. Align vol T type, used to indicate an alignment requirement using new and delete functions if it is greater than default new alignment flag. It allows to supply an argument for correct function overloading rather than size t argument, which is used to specify the address at which to allocate memory.
One interesting note. There seems to be a debate whether unaligned data incurs a runtime performance loss. Tests have been reported showing that it is in fact possible. To further complicate the matters, single instruction multiple data commands for Intel processors operating on unaligned data contain a speedup trick which turns them into their aligned equivalents if the data they're operating on is aligned. It is therefore quite a tricky task to perform impartial experimental evaluation of the aligned versus unaligned performance. I think it is best to do speed or memory measurements on the concrete system where it can actually matter, and then to decide whether to go for speed or memory efficiency. To sum up, in this video, we've looked at data alignment and what tools can we use to take advantage of it in C++ programming language. I have linked to the full article in the description below, and I highly encourage you to check it out. It contains cool graphics, descriptive code, and everything. If you liked the video, please consider hitting the thumbs up button and subscribing to the channel. Thanks for watching and see you in the next one.